So the first kind of problems that we will deal would be on the reservoir sizing. So what this reservoir sizing is, we learned two methods. One was sequent peak algorithm and another one was, what was the name of the curve that we drew?
Flow mass.
Flow mass curve, right? So you clearly saw that in flow mass curve, we were looking for some cumulative inflows and then using a constant demand line wherever distance was maximum, we were saying this is the capacity we need for a particular reservoir. However, in sequent peak algorithm, we were using some tables. That is, we can say that we will look for maximum deficit at any time t, right? And that maximum deficit should be deficit at previous time step, whatever you have, plus you may create more deficit by releasing water if you have more demand, minus what is inflowing. So basically you only have, last time you had a deficit of 5, now people are asking for 5 more units of water and you only got 2 units of rainfall. So your deficit will increase. It would become 8 basically, because 5 was the deficit from previous time step. 5 more units of water you have to release, only 2 entered into the system. So your deficit becomes 8. And when you have an opportunity to design a reservoir, you should design a reservoir for 8 units of water, because 5 is going to be insufficient just at next step. Does it make sense? So that's what we were doing in sequent peak algorithm. And we would say that if this is positive, this would hold true. And if this entire term is negative, then you really don't need a reservoir, right? So this becomes the compact form of sequent peak algorithm. That is, what is the maximum capacity, and in other case, what we are not going to have any deficit, so it should be 0. Deficit cannot be negative. Okay. Now what we will do here, we will try to include more interesting relationships and account for more variable flow into our formulations. So what we mean by that, can we say that we want to take that solution which is maximum of 0 or maximum of KT? This becomes a solution, right? Where KT is 0, KT minus 1 plus RT minus QT, right? And you need some boundary conditions. That means you can say that when we starting the cycle, we can assume that reservoir is not existent and hence it is empty, right? And then we keep on going in a tabular form and we solve it. Now, if you see here, this is a very straightforward problem. Real life problems would have more complexities than this. There would be certain demands, there would be certain releases, there would be some evaporative losses. Evaporative losses would be non-linear or dependent upon storages, right? And sometimes we may have to release or water which is always meeting the demand. So your release has to be always greater than equal to demand. Then there would be some spillovers. For example, your reservoir gets full, right? Demand, we are saying, is that we are directing that water through some penstocks or through some pipes and it is reaching an end user. Spillway is a simpler case. When you just open gates of the dam, you cannot store more than that, and then that water will just go away from that area and it would not be used by the citizens, right? So basically accounting for all these constraints may not be possible in such simplistic framework. Specifically, when we are talking about reservoir operation, we also want to understand what would be my evaporative losses. So far, we have ignored all these evaporative losses. We have to account for spillovers. So Let us say that we have this dam. So we have some water here, right? The capacity for which you have designed this dam is 5 units. That's all it can hold. Okay. In a given month, you got 10 units of precipitation. There was a demand of 3 units. So this becomes our dt. This becomes our qt, what is incoming, right? This is our capacity at any time t. Let us say storage at beginning of this particular time was equal to 0. When this time period started, our storage was 0. Can you apply some common sense and tell me that how the operations would look like? You cannot force users to use more water, right? They will use what they wish to. Any idea?
Sir, so first 3 units of DT will be supplied,
Okay.
and then 2 units of DT will be spillover,
Units will be spillover
and the remaining 5 units will be there.
and 5 units will be stored for the next step. This is how you will apply a common sense and operate this tab, right? And we have to reflect that into mathematical formulation somewhere. So we will not forget this spillover. There would be two things: release always includes whatever we can meet as demand plus spillover. This is what is getting released from this reservoir, right? We want to meet the demands. We will ensure that our at any time your release is greater than equal to dt, which is the case, right? Because your storage cannot be negative. Your spillover, so this is spill, sp, I will not confuse it with storage. Your spillover cannot be negative, right? So that is for sure that this makes sense. Enough. Now, do you want to maximize your spillover or minimize your spillover?
Minimize.
Why?
That like we can consider that that water would be wasted, or in some else we can say that thing. So
So you can, in some way, you can say that at least for that particular point of concern, that would be wasted. It may be useful for downstream communities. That's a different story. But ultimately, we are modeling a system. We have to restrict our thought somewhere, right? We cannot. You can. Their argument can go always back and forth whenever it comes to water. But ultimately, it's for that point that we are looking into the system. Makes sense. Okay. So this is what we are going to learn in next few lectures. That is how we can determine the capacity determination of a reservoir in more realistic way, account for real world constraints, and then we will also use some dynamic programming to look into reservoir operation, capacity planning, and benefit maximization. And finally, you would see that this qt is not going to be a number. You don't know in this month what is the amount of precipitation you are going to get. Can you tell me how many units of precipitation we will receive? What can you tell me about that part, precipitation?
So it can be anything.
It can be
Anything.
it can be
We
anything.
cannot predict beforehand.
Sir, but
To some extent, we can.
Okay, we cannot
yeah,
predict. Okay, I will take
sir,
it. We cannot predict.
sir, I was
Then
saying we can means consider it in a range, considering the previous data over the years. You might get
well,
an idea.
we cannot predict. Good options. Anything else? Think about it.
So forecasting, like that.
Huh?
Forecasting.
We can use some forecasting. What is forecasting? Can you tell us a little bit more about forecasting?
So predicting the weather condition based on the previous data for the previous months or the trend which that follows.
Can you say that what is the probability of having something in state t given what was the state t minus 1, t minus 2, and so on?
Yes.
Isn't it the word called as probability is exactly like that? From probability, you can estimate or forecast, right? So this is called as deterministic system. You know that this is 10, then 10 is 10. 10 cannot be 10.111. You know it is 10. Finished. Story finished. Right? Here, you can only assign probabilities. Right? So what is the probability I will become a billionaire in next 1 minute?
Zero.
Why I got this email from somebody saying that I won a lottery in Africa and he's asking for my phone number, which I'm planning to do, right? So that if it is not a spam, I will become a billionaire or billionaire, right? So zero, and how do you know that I haven't purchased a lottery ticket? I am going to win it. Whatever it is, it's a non-zero thing, right? But the estimate would be close to zero. I agree, because chance of that being not a spam or chance of winning a lottery is 1 in million or something, or 1 in billion. I don't know. So my ultimate expectation to become a billionaire is going to be zero. I cannot go and book a luxury car that I'm going to be billionaire. I have some probabilities associated. So I cannot use that for making a decision. Right? Similarly, what is the probability that I'm going to go bankrupt next minute? Again, the probabilities are low, but I would not say non-zero because I really don't know how my life is going to turn out at the next second. So same is the case with precipitation. What is the probability that there is going to be a storm in your city in next 1 day? Yes, it is closer to zero, but completely ruling it out is also not a good idea, right? There are something called as gray swans or black swans, and you never know. There is a cloud burst and there is a flooding, right? So basically, but you would not prepare your tomorrow for that. You would plan for some mean event. Yes, I know it's a month of October and probability of getting a heavy rainfall somewhere in North India is low because monsoons have gone away. So I should not carry my umbrella. However, if you are going out in month of May or June or July when monsoons are at peak, even if clouds are there and sky and it is not pouring, you will take out your umbrella. You never know when it is going to rain. So we call that, instead of determinism, we always live in a stochastic environment. And we have to plan for various probabilities. We have to make decision for various probabilities. And that is where I need to take care of the extremes of the events. And I should know that what is reliability of my structure. I should know what is the dependency of my structure, be it hydraulic, be it hydrologic, be it any engineering structure that we are dealing with. And this is a big difference that we as civil engineers deal with in comparison to a controlled environment in industry. Right? Industry is a controlled setup. You know that if input to this machine is this much, this is going to be the output. And despite that, accidents happen. There are gas leakages, there are pressure outbursts that take place in industries. Right? Because there is also a small amount of reliability associated with so many components that are working in series or in parallel. However, in natural systems, that stochasticity is manifold. We are always preparing for that. We are always designing for that. Right? For example, again, if we take an example of a production line, Maruti or Honda or whatever company, it would know that tomorrow they are going to produce 20,000 or 30,000 units of cars from plant located in Chennai. They more or less operate in a deterministic mode. But at Sardar Sarovar Dam, we would never know what is the exact quantity of water we are going to get tomorrow. And ultimately, at the downstream, we both are optimizing. They are optimizing or maximizing their profits at the minimum resources. We are minimizing the damages or maximizing the returns, but operating under a different stochasticity. And needless to say, the leap from determinism to stochastic thinking is going to be little bit tricky, little bit difficult. And that's where we said that we slowly and steadily will transit from easy to difficult topics. But it would be good for you to develop a good flavor for that stochasticity in next few weeks. Does it make sense so far? So let us start writing that we have to first of all do this reservoir capacity problem using linear programming. Now you guys are familiar with linear programming, and I'm sure that Gecko questions worked out well. You got a good experience with Gecko, and you found that it is good enough for this class at least to solve these problems. And not even this class, it is even good beyond. Chemical engineering industry use Gecko out of the box once they know the process. Okay, but ultimately Gecko would not tell you what are the constraints and what are the objectives. That thing has not been made easy by any computer programming for us. You need to tell very clearly what is your objective, what are your constraints, and it can just tell you whether it is solvable or not. Now, if we talk about sequent peak algorithm, what is our objective? Forget about sequent peak algorithm. Whenever we are talking about size or capacity determination in reservoir planning, what is your objective? What you want to minimize or maximize? You will talk, I will just listen and write. What are your thought processes?
So minimize reservoir capacity.
Minimize the reservoir capacity. Very good. Minimize KA. Because you know that if you can build an infinite size dam, it is always going to make sure continuity is satisfied, but who is going to pay for it? So you want to minimize that. What are the constraints subjected
So
to?
the active storage should always be less than equal to maximum.
Makes sense. ST should be less than equal to KA. Absolutely right.
So,
What else?
and both these values should be positive. ST
ST
and K.
should be greater than 0. KA should be greater than 0. What else?
We can apply mass balance, that storage in the present time should be equal to storage in the previous period.
Okay. Storage at
Plus inflow minus 1, ST equal to ST minus 1.
so ST plus QT minus
RT
RT
minus
is equal.
NT losses.
Sorry, watching the notes.
Some losses
Amit,
like evaporation losses or any other losses.
but your terminology exactly matches our book or reference book that we are using. So losses. What are the losses here?
So the evaporative losses or
Do we consider the spillovers in this losses?
That will be considered in releases. Right?
Sir, I
You
have
always notes. So it's my request that if you are referring to some book or notes, please close it, because we should take it as a fun exercise. You can always watch. There are so many resources, but the problem is that it will not provoke the thought that we are going to provoke ourselves. Right? So let's enjoy that exercise rather than going back and forth from books and notes. Yes.
sir, in some I saw some of the textbooks in that it is release is taken just to satisfy the demands and spillover is taken separately. So in that condition, release is released, they have applied the constraint RT should be always less than equal to DT.
Yes,
Because they are
that's exactly what I stated, right? So depending upon how you are defining the terminology, right, all your constraints can change, and that's where I cannot compare one solution just to another here. But from continuity perspective, this is true, right? ST plus QT minus release minus LT, because you know hydrology now, right? That's what we have been doing. Does it make sense?
Yes, sir.
Anything else that we have missed here? So now how we can solve it? First of all, we need to look into losses. How to write evaporative losses? What is ET? Now there is a certain methods which your notes that you are referring to will not talk about, but we will talk about here, right? How to calculate evaporation? What are the units of evaporation? And in real world, if I just leave you to reservoir, how you will get yourself out of the situation and come up with the capacity determination, right? So evaporation at any particular place is measured in per day. It has a unit of rate, right? However, you would have storages. You are at reservoir, you are standing at Sardar Sarovar Dam, and you have all the money in the world. Whatever you want to measure, you can measure. What would be the easier things for you to measure? So this is per day. All your flows calculations are in meter cube, millimeter cube, million meter cube, or megameter cube, whatever you are calling it. So you're going to bridge this gap of the units. Let's apply some thought there.
Change in height of a water level.
Huh?
Change in height of the water level means
Okay.
if we know the area, then we can easily do this.
If you know the area, you can say you can measure change in height. Very interesting point, Shazib. What is depth of Sardar Sarovar Dam? We had this discussion in our earlier class. Somebody said 122 meter, right? Something around that. 120, 120, 130 meter. What is the typical amount of evaporation that happens?
So it is very less, but we
In
actually do
7.9 per day, 8 per day. So it would be even just a rounding of error if you look from the dam height perspective. But what is area of a dam? I told about this backwater of what was the dam? Bhakra Dam. It goes all the way to 90 kilometers. Right? So it's a big issue of scale. What we typically ignore as a rounding of error in other fields, it becomes a big quantity for us, which we cannot just overlook. Right? So that means that just using that gauges to measure evaporation would not work. But that being said, it is a method which motivated us to set up all the equations. But we apply that equations and we call this set of equations as Penman's equations. And we also have subset of energy balance equations, aerodynamic method, and so on. And you must have learned it in your hydrology classes, right? So, Dhruvi, do you remember this?
Yes, sir. Somewhat.
Oh, What are the typical inputs for that? You would need temperature, you would need
Temperature,
humidity, right? You
fresh,
would need wind speed,
wind velocity.
yeah, wind speed and so on. You would also need your location because you have to calculate how much solar energy you are going to receive at that location. Because even if temperature, humidity, wind speed are same at North Pole and in Gujarat, the angle at which solar radiation is falling is going to be very different, right? So it becomes a very localized factor. But good thing is that when you look into all these parameters, there is a recommendation which exists in FAO chapter 2. From FAO chapter 2, you can easily determine that if I tell you the location and give all these meteorological data to you, you should be able to tell me what is the rate of evaporation for 1 meter square of water at a given place. And that typically comes out to be in unit of 7.96 per day if we are talking about tropical country like India and so on. And then there is some seasonality associated. In winters, this value has to be lesser in comparison to summer. Needless to say why, because the amount of energy that is incident is higher and so on, right? But one thing is for sure that we can get here. I will not go into details here. For that, I will post links to my videos on evaporation. If you wish, you can watch them. But ultimately, let us say that we know it from a local condition, ET. Now, the problem here is it may be easier for us to determine the storage, the amount of water that is stored in that particular area, right? If you are not having any topological or topographical maps, right? Because what is storage? Storage can be determined from continuity equation. If I give you all the hydrographs is variation of water with respect to time. How much water is coming into your reservoir with respect to time? That's a hydrograph. And if you take area under this hydrograph, what that is, isn't it storage? Or it's a volume of water. This unit is meter cube per second. You are multiplying it with second. Ultimately, you end up with meter cube. So if you know that how the inflow characteristics look like in a given watershed because of a storm, getting into meter cube is not a problem. But again, the problem comes is that I know ET. I know the rate of evaporation, small ET. Its unit is per day. I can determine storage. Unit of storage is cube. So I can say that instead of I can say it is meter. If I know I know meter, right? Not a rocket science again. But if I multiply ET by S, I'm not going to get anything. It is going to be 4, doesn't make any significance, right? Even dimensionality doesn't make any sense. Forget about the variable. What we should do with this ET to determine the losses in volume. I am always interested how many kgs of water is lost. Let us put it that way. What I should do, how I should go ahead with that. What is missing, but I need.
Density better.
Bhaumik, again, I'm not too much worried about kg to meter cube calculations. I can do that. But ultimately, I don't have anything in meter cube. I have total storage. I know fraction of it would be lost as evaporation. But ultimately, how to calculate that fraction? That is my ultimate problem. I cannot just assume 10%, 15%. It would be a very wrong estimate because the quantities have increased so much that 10% of a few mega million or mega meter cube is going to be huge quantity, right? Any thoughts?
Can we include area or something then?
Yeah, we need to have area if we want to bring in evaporation into picture. Area of what
Um,
now?
Maybe we can consider unit area something.
But unit area would not work because all your calculations are in absolute quantities. You are optimizing releases. Release is in ultimately you are using water at 150 liter per capita per day. So the problem here, that's exactly what we are trying to highlight, is there are so many heterogeneities now that we cannot assume anything per unit area. That's why we have to work with exact quantities. In hydrology, it was easy for us. Let us assume that width of a channel is 1 meter, or let us assume area of watershed is equal to 1 meter square. Because there we are not having heterogeneous quantities. Basically, we say, okay, now if we know this, we multiply it by area, we will get our volume. But here our users are into picture who are using water in liter per capita per day. This is something very interesting that you should think about in next couple of minutes before we proceed ahead.
Sir, can we consider surface area of reservoir?
Yep, you are getting there. We should consider surface area. Now there is an interesting problem. In your typical class, what professor would say, including me, and that's what I do in hydrology, is let us assume that it's a rectangle, right? If you know somehow depth of the water, you would know that what if the volume is known, area is easy to determine. But let's go to real world dam. How it will look like? Something like this. They are made at the bottom of rocks or mountains. You would not find dam just anywhere. I'm not talking about the small dams. I'm talking about Bhakra Dam and dams, Sardar Sarovar Dam. Have you been to Sardar Sarovar Dam? It's a beautiful place, right? If you go to upstream, there are some boat rides. Take that boat ride and they will take you to upstream in the mountains. Then you will see, wow, this is an entirely different world from where this water is coming, right? And below that, your terrain is also going to be non-linear. Right? What we should do, because if water is here, area is going to be different. If water is here, area is going to be different. If water is here, area is going to be different. There's a problem then. What we should do? So put your engineering hat, right? I always say that, yes.
Like which area are you talking about? Like basically when evaporation, it will always occur from the top surface.
Evaporation will always take place from top surface.
So like what area other, I mean, I didn't get that point, like considering this.
Level of water. So when storage would change with respect to time,
Okay.
surface area should change. Sometimes water would be here, sometimes it would be here. So every month your rate of evaporation in discharges would be different. And so would be this area.
So area will depend on the storage level.
Yeah,
If
area would
storage level
depend.
change,
Absolutely fantastic. Area would depend upon storage.
because if storage decreases, area will decrease.
So now another problem arises. Would it depend upon storage just, or would it depend upon storage square? Would it depend upon log of storage? Would it depend upon exponential of storage? I have kept your statement, right? It is dependent. I totally agree. But all of them are going to yield a different result. You agree? And it is again not going to be a negligible error.
So based on the data, we can fit a regression curve and find out.
Okay. So I hope Raviraj, you are sitting without notes, right? Raviraj?
Yes, sir. Because if area changes, then we can also get storage at some point. So if we get,
Yeah.
if we consider upper surface, then for that part area will be there, and storage we know. And if we go down, if we, the storage decreases, then area will also decrease. So if we get multiple points, then we can establish relation.
Yeah, I'm saying that you are not using nodes, right?
Yes, sir.
You are using nodes.
Which note, sir?
Okay, you don't even know the nodes. Okay, then good. You are not using them. Okay, that's exactly what we will do. Whenever we'll get a chance, we will plot area versus storage relationship. You go to a dam, you need some data. Ultimately, you're solving an engineering problem. Rather than just making a guess, it's A proportional to S, A proportional to S square, A log of S. It's a bad guess to make, first of all. Do you agree with me? Get the data, plot the data, see the behavior. Now, if you know the storage based on your hydrological understanding, you can quickly determine what is the area. Right? And we call these as stage storage relationship. Stage is height, storage is storage, relationship is their relationship, how they vary. Does it make sense? So if this is clear, then you would find no difficulty in understanding this concept, which otherwise proves to be tricky sometimes.
So can
Now
the
another,
topographic map help here in any way?
absolutely, absolutely, but you need to do the same thing again. So once you people actually use topographic maps to develop these relationships, because when you see a full reservoir from the top, you would have no idea how the terrain is. So you would wait water to recede and come back, and again you will again make multiple observations. And you will say, okay, if water is up to this height, this is the area which I have developed from topographic map. This area is actually coming from topographic map. There is no other way to determine the area. You do drone surveys, people also do planimetric surveys when drones were not there, right? So people would plot them on a topo sheet. Topo sheet means it's sort of a graph paper which is drawn, and the entire diagram is drawn to some scale, and you will take the measurements there, right? So if you go to Bhakra Dam, I've been there, and if you get access to their control office, which generally they will not give unless you go with some credentials, there they will show you all the topo sheets. I mean the size of topo sheet is as big as your classroom. So, and then they will have each and every detail of contour line, from where water is flowing, what is the direction of maximum flow, because that's what they have to plan for. What seems to be a very simple operation, it's an engineering sophistication, right? And in topo sheet, you will have sort of full terrain map, because before they started building the dam, they had a better control of the area, because water was not there on day zero. They would stop the water and let water accumulate, right? That's where these first topo maps were drawn, when they do reconnaissance or land surveys. Now let us say that we now, for sake of simplicity, we find enough points and we find that this is a straight line. Just putting, it could be anything. I'm just saying that for sake of simplicity, I'm saying it's a straight line in the simplest case. I can say that my storage is proportional to area, or my area is proportional to storage. If my A is dependent variable and S is not, then A is proportional to S. Can I say that A equal to KS without any loss of generalization? Can I also say that A is equal to KS plus C without loss of generalization? Because Y is equal to MX plus C, right? Same equation. So that would mean that give me a storage, I should be able to determine area given that I know this K. And this C is interesting. This C is, of course, it's an intercept. But the way we calculate this intercept is little bit different, and I want to bring your attention to that. Let us say that we have a reservoir here. We have some terrain here. There is some storage below which water cannot go, because you would not take water from dead zero level. You will always withdraw water from a reservoir at some level above the ground. Can you tell me the reason why that's so? Ashwani,
Yes, sir.
why you will withdraw water from somewhere here, and what would be the preferred point for you to draw water from a dam? A, B, or C?
I guess A.
Why?
Sir, because no matter what the water level is, A will always have the water.
Okay, no matter. So your reliability of withdrawing water would be high. Excellent point, but absolutely wrong. We'll talk about that, but that's what my common sense would also say. Anybody else whose cameras are off? Ravi,
So any point A and
please,
C.
please try to turn on your camera. Otherwise, it feels like you all are cheating. It cannot be the possibility that bandwidth is low simultaneously throughout India from 11:30 to 1 on Saturdays. Right? Yes, now I can see many faces coming up. That means bandwidth is fine. Rachna, what would be your preference point? If you have to, so basically dam, we have to withdraw water, right? From where we should draw water? You're on mute. A, B, or C? Renzi, you have learned some hydrology. So that's what you would do in JE, right? C is definitely ruled out, right? At least it has to be A or B. But think of a real world challenge, that what could be an issue between A and B that nobody is going to tell us when you go to field or try to execute a project. You have to apply some general thinking.
So that is related to hydropower.
Even basic than that.
Sir, accumulation of sediments.
Yeah, who is this?
Sir, this is Diptija.
Diptija, yes, you are absolutely right. Whenever water flows, water just doesn't flow alone. It will bring lot of sediments from the top, right? So this will bring all the debris from here and deposit here where it slows down. If I put my pipe or penstock here, it will get choked. This dam would be just useless for me. And there have been instances, what appears to be common sense is not so common. There have been instances where dams have been built without accounting for sedimentation load or underestimating the sedimentation load, and entire hydropower plant became non-operational. Right? And the problem is, it's not just it's not like a turn on or turn off. Whenever turbines, they have to stop. Right? It's not easy to stop a turbine. Can you imagine why? Because you are converting entire potential energy into a kinetic energy, right? That's the operation of dam. mgh equal to half kV square. You rotate the dam, you rotate the turbine, and you generate energy. Now that amount of potential energy, it has already entered into your system. Every time there would be some water, you're not putting a gate here. You cannot just put a gate here, a small gate, and assume, okay, things will work back. There is going to be an instant loss. There has to be an instant onset of impulse. If you recall, impulse is rate change of force with respect to time, where a delta tends to 0. Right? So just beyond these structures, we usually provide something called as a surge tank. So the depth of surge tank ranges all the way from 30 meters to 100 meters. Things look simple, right? 30 meters, that's fine. You are at base of a mountain, because these dams, if it is a natural cut dam, it would be typically at base of a mountain. You go below Himalayas and you dig a tunnel down 30 meter or 100 meter, just to absorb that water whenever sedimentation load becomes higher, so that we can turn off the operation safely. And we will talk about hydropower generation, optimizing that. And that is where these small A versus B becomes a deal maker or deal breaker, where we should position that. Right? And in this case, this would constitute our dead storage. That no matter what, do not take out water from dead storage. Be it full of sediment, be it full of water, do not take water from dead storage. Make sense? If it makes sense, what we do, we use this dead storage, and instead of drawing curve for entire section, we draw the curve just for this section. That means now we can assume, if we know the surface of dead storage, we can extend this upward and say that this A naught is always going to be present. My only worry is this extra water that is coming between this nonlinear structure. Does it make sense? So we can say that my surface, or the total amount of evaporation that is going to take place at any time t, right? It is going to be ET, the rate that you have determined using Penman, Monteith, or any equation or aerodynamic method of evaporation, evapotranspiration. But let us say this is known to us based on various climatic factors. Multiply by A naught plus some storage multiply by that coefficient, which we were saying this is M, the intercept, or the slope of the regression line that you have drawn. Because you said that y is equal to mx plus c, right? And now this intercept is going to be 0, because when here our storage is 0, then there is no point in worrying about the surface area also. Right? So basically we can simply multiply it by the intercept, or the relationship that we have developed here. If this slope is, let us say, m, we can simply say that if I know storage, I know m. If I know storage and I know m, I can determine what is the surface area. So this together becomes surface area of live storage. Does it make sense? And now again I multiply it with ET, the rate of evaporation. Now this is surface area multiplied by rate of evaporation should give me the volume of water that would get evaporated on a given day t. Does it make sense? If you have any questions, ask me, because you know these are fundamentals, and after that you know how to handle this, because formulating this constraint is the hardest part from now on. So every concept should be very clear to you, and doesn't matter which book you read, you should be able to know why they are using RT, why they are using DT, and those questions would automatically go away then. Now question arises, which storage we should use? You are estimating evaporation in month of December. or not December, let's go to monsoons. You are estimating evaporation for month of July. Okay. In June, just at the end of June, there was no water into your reservoir. It could happen in India, so much higher rate of transpiration and so on, evaporation. A lot of monsoons happen. So storage at the end of June was 0. Storage at end of July was 300. Makes sense, right? Indian context, monsoons happened, reservoir is full, storage increased. What should we do? 1 month, two values. फिर से फंस गए.
Average works or
Yes, you have to be confident. That is the best guess you can have here. Average works. I don't have any other information. Average works under an assumption that rainfall was increasing uniformly. Not a bad assumption in case you don't have any other data. Right? You will just have monthly data and you say, yeah, that's the best guess I can make. Now, my ET is accounted for. So can I write, instead of now being consistent with the book and the notes that I am following for our lectures, I will use this A, but A is equivalent to the slope of that line. Let's think about that. So this is our ET. Can you write a continuity equation now? That how it will look like? By accounting for ET. Can I say that ST plus QT minus RT, release is release, total release for our discussions, minus ET is equal to ST plus 1. There would be one more loss, by the way, which we have altogether ignored. That would be groundwater loss. कोई concrete पे तो बनी नहीं है डैम, नीचे तो मिट्टी ही है, right? And if you put water on top of soil, water will try to find its way to flow through that. But yeah, we are ignoring that, and let's be very clear with that assumption, right? Because that would add another level of complexity, and it has been shown that whenever dams are built and after a time that soil reaches saturation and the losses becomes negligible. Now my question arises, can you tell me the simplified expression such that all terms of storages are on this side? This is ST, and all other terms are on other side. Can you simplify it and tell me the final expression? Even if you are sleeping, I will ask somebody whose camera is off. I'm sure mics will work. Determine the coefficients or simplify this equation, and then we will go from here. Any success? Anyone? how your final continuity equation looks like. Shazib,
Uh, Sir, ST bracket then 1 minus A by 2 into then plus QT minus RT equals to
just
ST.
a minute, just a minute, just a minute. You can further simplify. Let us assume that A multiplied by ET by 2 is equal to AT. We don't want to deal with any fractions. We are just saying that we can put this together into another simplified term AT. फिर थोड़ा सा और simplify करो इसको. Because we have to ultimately write a code in Gecko.
Sir, just a small question. Sometimes I means on internet I saw that they put a large number of black balls on the water. So
Yeah.
the evaporation will be very less. So I think do we have counted that thing while making the graph of storage versus area?
No,
Is
we have not counted for that because that is very costly practice and it is generally not followed in India.
okay.
And not only this, they also put a layer of a chemical,
Hmm.
right? I think I also taught it when we were talking about hydrology.
Yes,
I
sir.
taught the
From hydrology lecture, I remember that some chemical reaction goes there, and a large number of
not
black
chemical
balls are
reaction.
there.
They just put a layer of oil, which is
Hmm.
non-harmful to the marine life, but it will stay afloat and it doesn't evaporate. That also minimizes the
Evaporation.
rate of evaporation. But
Hmm.
no, we have not accounted for.
Okay.
And if you want to account for, you ignore ET. But ultimately, Sardar Sarovar Dam. So all these studies that the notes that I'm designing or the reference material I'm referring to, I'm contextualizing everything for that dam.
Hmm.
Okay, so that we have some, we solve the worst case scenario and everything after that seems easier. That's how we should approach this.
Yes, sir.
Anybody should not have taken that much time.
Yes, so ST plus 1 would have the coefficient of 1 plus 80.
Absolutely right.
ST minus 1 would have the coefficient of minus of 1 minus 80.
So if we have ST plus 1, we should have ST here, not ST minus 1.
Sorry, ST. Yeah.
Yeah. So this would be 1
Minus
minus 8.
80. Yeah, with a minus sign outside.
Yes, with a minus sign. Or let us write it on other side again. These were the only two coefficients that we were interested in. So this becomes 1 plus 80. This becomes 1 minus 80 into ST plus QT minus LT minus RT. This LT is nothing but it's the ET8 naught, right? Just for sake of simplification and to be consistent with our notation of our textbook, that's what I'm using. Sounds good so far? अगर हम इसको derive ना करते, this would have been very intimidating formula कि what is A, what is T, but now you know it's not nothing rocket science. It's a linearization of a system. Does it make sense? Now we can write again all the constraints. We have to make sure that this continuity equation is always followed. Array. So this is for sure. This is subjected to. You have to minimize K capacity. That's it. You have to minimize K. Subjected to this constraint. This is most fundamental constraint. What other constraints you want to have?
ST will be less than or equal to K.
ST Has to be less than equal to k. What other constraints you want to have?
Both will be greater than 0. Yes.
SK has to be greater than 0, k has to be greater than 0. What other constraints you want to have? Reservoir बना किसके लिए रहे हो? Why are you making a reservoir?
Sir, release should be greater than or equal to demand.
Release should be greater than equal to demand at any time t.
Sir, storage height should be greater than or equal to some constant, like we have to, if we have to generate electric something, so there should be minimum height that we have.
Totally agree. We will talk about, so far we haven't brought hydroelectric into picture, but you are absolutely right, and we will do those questions separately, and then we will combine these two. Right now our objective is only to meet demands, making sure our system is physically consistent. You are absolutely right, and that needs a special place in our discussion. But so far, let us say that it is just for drinking water purpose. No electricity would be generated. Anything we missed? That's it. These are the only constraints that we have to worry about. If you cannot think about it, right, and you are sure that you have covered all consistencies, we should stop. That's it. Now, my question to you is, I don't really like equality constraints that much. I hate equality constraints. I have already talked to you about that. Why? Why we hate equality constraints? Anyone? Shubham?
Sir, no
Why
idea.
do we? अरे यार सिंप्लेक्स में याद करो क्या होता था जब इक्वालिटी कंस्ट्रेंट आ जाता था.
सर
कभी आर्टिफिशियल वेरिएबल लाओगे, फिर उसको
हाँ
डमी बनाओगे, उसको एलिमिनेट करोगे, नहीं होगा तो इनफिजिबिलिटी आ जाएगी, राइट? दैट वाज
हाँ
द issue there in simplex. Remember that?
yes sir, yes sir.
Same problem here. That's why I don't like equality constraints.
So but here won't it give us a definite answer, means regarding the
In real
regarding a
world,
condition?
Shubham, you are absolutely right. In real world, it will give us a definite answer. But doesn't simplex method also at the end gives you a definite answer? It doesn't leave you with a
Yeah.
range.
Hmm.
But you still have a feasibility space and you pick the best out of that feasibility. We talked about basic feasible solution and basic feasible optimal solution. It is better to have a basic physical non-optimal solution rather than having the best best or quote unquote optimal non-feasible solution, right? You should get 100 out of 100 in all the courses that you are taking. Best solution, non-feasible, right? You should get 90 plus in all the courses such that you get A grade, because 100 is not going to change anything in terms of your grade, and amount of effort that is required just to get 90 and 100 is significantly different. Basic, feasible, optimal solution, right? May not be the best, but yeah, works in under time constraints. So think from that perspective also. So what I can say is that my release can only happen in two cases. There has to be some spillover or there has to be dt. अगर ये रावी बताएगी, रावी is silent today, so she has to answer this. If we have to replace this RT by dt, what should happen to this sign? Right now this is equality sign. I want to replace RT by DT. What should happen to this equality sign?
सर लेस देन इक्वल टू हो जाएगा.
किस तरफ लेस देन इक्वल टू आएगा?
मतलब किसी ऑर्डर में लेस देन इक्वल टू 1 प्लस एस टी प्लस 1 वाला. हाँ,
ए आएगा या बी आएगा?
ए आएगा.
ओके, पक्की बात.
हाँ, क्योंकि आरटी बड़ा है तो पहले ज्यादा कम हो रहा था, अब कम कम हो रहा है तो.
You're right. This is correct. ए आएगा. राइट? अब जो टेक्स्ट बुक्स थी वो यही करती हैं. They would not tell you why they have replaced RT by DT, but they will do it, and then you would be left wondering why they are doing it. This is a positive quantity. You have replaced it, and hence the sign should be greater than equal to. Had this been a negative quantity, it has to be less than equal to. So I can also write this as this. Not going to hurt me anytime.
सर
Yes.
सर एक और केस भी हो सकता है ना, जब रिलीज करने के लिए उतना वाटर अवेलेबल ही नहीं है, मतलब डिमांड के जितना. वी डोंट हैव दैट मच वाटर, तो जितना भी रिलीज होगा उतना हमें एज पर डिमांड वी हैव टू गिव आउट.
Okay. So that means this particular system is only solvable when your sum of inflows is greater than equal to sum of demand. You're not designing a standard operating policy, right? You are designing an optimal operating policy, right? So you are saying that your release has to be greater than equal to demand. Under an assumption, this is only solvable if at any point time t, right, you don't have enough water to meet the demands, then it's a problem. That means your K has not taken care of that. Does it make sense? Your storage is also less than equal to K. Your K is also less than equal to 0. Right? So that's what this optimization should exactly take care of. It is just doing a distribution of water in time. So that situation should never arise once you solve this optimization that you don't have water to meet the demands. Because total amount of money that you are earning is more. In a given year, total amount of money that you are earning is more than your expenditure. Does it make sense, Bhomik?
Yes, sir.
That is the first assumption, only then you should build a dam. Now you say that I have expense of, and you are solving these in steady states. Steady states means that you are certain that okay, this will operate under these conditions. No variations are allowed. That it could happen in a given year that condition that you are earning may be lower than your spending. But steady state means these two conditions are always true throughout life of the dam.
So steady state is in since it's dynamic, it's changing with the time.
So let me put quote unquote steady state. Steady state from the operational point of view. That means we are not saying that in any year the demand can be greater than. So this is
overall
not,
in general.
Yeah, this is not this steady state. The steady state from operational perspective. That now you have joined a fixed job, fixed salary job. That put it like that. But in given year, you could have more expenses on your health or for insurance needs and so on. But in general, steady state is, yes, my salary is more than my expenditures. So if I have to spend more in January, I should have buffer for that, which I have created in other months. Does it make sense?
So all in all, that the reservoir capacity should be such that it will take care of the surplus water or the surplus, like it should have a particular amount of water so that all releases are maintained.
Yes, you should always have that amount of water that your releases are always taken care of.
Okay.
Right? But what would be the amount of spillway? What would be the amount of spillover at any time t?
So it would be the excess of the reservoir capacity.
Okay, but we have to
X
write formula
plus,
for that. We have to write formula for that at time t, because now we are putting everything in mathematical context. How much water would
any
spill?
excess water above water capacity,
No, no, no.
reservoir capacity.
Tell me everything in terms of ST 1 minus AT. So also ST plus 1, which will have this coefficient. Yeah, ये coefficient इसके साथ चिपक गया है, something like that. What would be the spillover? Put that into this formula. Anyone? ये डैम वही वाला एग्जांपल याद करो यार, स्पिल ओवर जब कैसे किया था हमने, हाउ डिड वी डू स्पिल ओवर? हाउ मच वाटर विल गेट स्पिल्ड ओवर? एसटी था, क्यूटी था, लॉसेस थे, कुछ डिमांड में चला गया, माइनस एसटी प्लस 1 कुछ टाइम नेक्स्ट स्टोरेज में चला गया, minus k, where k is the capacity. Isn't that right? Same example, 13 units of water is coming. Then what if this is greater than 0? This should be the amount that is spilling over. This takes care of current time. This takes care of future time. Right? If at current time you have 10 units of water, you know that storage at next time unit is going to be 13. Right? Your capacity of dam is 20 units. How much water you need to spill over? Your storage at time t is 10. Some water should be inflowing to meet this. Make sure that this is 30. You don't need any spillover. As simple as that. You would only do spillover when your dam becomes full. Right? So 10 units of water was present. Now 30 units of precipitation happened. 5 unit was the demand. And you know that at ST plus 1, your amount of water that is present somehow is up to capacity of dam. In this case, we have started with 10. You need to do some spillover. Don't you agree with me? Because 40 units of water, it entered into the system. Your demand is only 10. Your storage is only 10. That means ST plus 1 has to be maximum it can take is the value of 10. And you have already specified that ST plus 1 has to be less than equal to K. Even if it is at a maximum value, total amount of water that you have to take care is 35 minus 10, 25. What should be the spillover? Whatever is excess, whatever you cannot store at this particular time, it has to be spillover. That is where we say that it becomes spillover, simply becomes whatever you have the deficit from your quantity equation, whatever is flowing out is a spillover. So it becomes 1 minus AT multiplied by ST plus QT minus LT minus demand minus AT into ST plus 1 minus K. That's it. This is the amount that should be spilled over. What do you want to do with spillover? You want to maximize it or minimize it? What do you want to do with spillover? Maximize or minimize?
Minimize.
Huh?
Minimize.
Minimize for which month? It's a function of time, right?
Every
Can I say that sum of spillover? Make sense? Now this system of equation, just because of addition of dt, it became complicated. Think about it. Because initially you were having a very simple la la land kind of scenario. There is no spillover. Let me just think of release. Let's not think of any other complicacy of a system. As soon as you ensure that no, wait a minute, I have to also account for spillovers which should be minimized, the complexity of system just increased. You had to spend some extra thought there how to write an equation for spillover. But ultimately you are just applying your common sense. A linear system hai, there is a bucket, right? You have 5 units of water there, you turn on the tap, 10 more units entered, capacity of that bucket is just 5 units, you drank 2 units of water. How much water would be spilling over? Not very hard problem if you think from a bucket perspective, right? You can always write equation for that. This is exactly the equation that I have written, right? And we solve this, we minimize this, and summation of this over time t, we should get a solution. Now question is, I have written all these constraints, and of course this spillover should always be greater than equal to 0. It cannot be negative, right? You cannot have water back into the dam. And it's important. You are writing a mathematical formula, by the way. These zero constraints become very important because your software would only don't know what problem you are solving. It will just give you an answer. Even for you can get right answer for wrong reasons. And that's where the zero is important. Does it make sense? Now, this is all good. You can always define a constraint. It may take 1 hour, 1.5 hours. That's not a problem. But ultimately, you're solving a problem at a scale of Bhakra Dam, and it should take time. And it is supposed to take time to write all the constraints, think about them, validate them. My question is, you will get the data in form of monthly time series or daily time series, that for November, for December, for January, for February, let us say, what is QT, what is RT that is coming in, right? So QT is the amount of inflow, precipitation that is falling. Let us say this is 30. DT, demand is known. Generally, you don't know the release, you know the demand in that particular area. So demand, if it is 10, this could be 15, this could be 20. It is increasing. I don't know why. This is 40, this is 30. First check you should always do whether your sum total of Q is greater than sum total of demand. Only then you need to think about all these complexities. If your Q is not equal to demand, or it's if your Q is lesser than demand, then you really don't need to solve all these optimization problem because solution would not exist. Why it would not exist? At some point, this constraint would be violated. You cannot always have a release greater than demand or equal to demand unless you have a buffer stock. Again, recall that salary example I am saying. In a given year, your expenses are 1 lakh rupees, your earning is 2 lakh rupees. Or, right, it could happen in 1 month you are just making around 20,000 rupees, and in that month you have to spend 40,000 rupees. That is fine because you already have a buffer stock, because you have saved somewhere else which you can use in that deficit month. That's why you should have a bank account. If your earning is 20,000, you are having an expenses of 50,000, should you open a fixed deposit in a bank? Right? Dam is our fixed deposit. and you are very honest government officer who take bribe every month, and you cannot store some money in your bank account, that would be your spillover. You have to spend it forcefully, right? Because as soon as you save that honestly earned bribe into your bank account, you would be caught and you would be spending rest of your life in jail, right? So spillover is exactly that, what you cannot store in your bank account. You will forcefully spend it, right? And that's what we are trying to quantify. Now you will have these equations for these months. Then you can always, if you know the initial conditions, you can always know that lower bound is always 0 and upper bound is something. You can always write this as minimize, first of all, minimize k subjected to S2 can be written in terms of S1, Q1, and A1, that evaporative losses and so on. We can expand that, right? We can write S3 as function of S2, Q2, A2, Q1. And in this case, these are linear functions. I'm doing nothing special. I'm just putting t equal to 1, t equal to 2, and so on. And I will do it for all the months. Does it make sense? Once I do it for all the months, I would have all these linear equations, which I can put in Gecko. Only number of equations have changed. They are all still linear equations. And ultimately, what I should do, let us say that we go to 12th month. How I should write equation for 13th month? यहाँ तो फंस गए. ये पता है हमें, we know that February would depend on January and February. That's right. S2 means February. It would depend on January and February. अरे continuity equation. March would depend on whatever was the condition in February as well as January and beginning or end of February, basically the storage that we would have beginning of ST plus 1. But what would about December? So you know that there would be two terms, ST plus 1 and ST. When I put T as 12, there are 12 months. If we are using same calendar, it would become S13. It would be function of ST. Huh?
First month, sir. 13 is first January again.
S13 would become January again. The assumption of cyclicity, calendars go cyclic. So this is the only catch. You will expand these systems, write it in Gecko, you will get the solution for 12 variables, you are done. And you will get the value for your K. And I hope you have not cheated in your exam and you have solved those questions yourself. So you know that how output would look like when you put it in Gecko. Can we solve it using linear programming algorithm in SciPy or MATLAB? Bhomik, you have worked with SciPy MATLAB before, you were saying, right?
Sir, I used SciPy linear programming for first question.
Can we solve this setup using that?
So if it doesn't, if it's a linear problem, if it's not non-linear, we can do that.
Yes, it is a linear program. It is a linear problem. So let me quickly show you before we end today's class. Let me change my screen. Can you see a screen? What are you seeing there? Because I cannot see what I'm sharing.
Example 1.
Example. Okay. So these are the notes. I will share this entire bundle with you. So this is the lecture template that I follow for this particular course, right? But there are a lot of mistakes, by the way, in these slides. So I would not let you fall into trap with that. So go with your understanding, whatever you understand. But examples and everything are borrowed from here. And this particular slide deck was designed, I think, 10-15 years ago. So all the methods to solve the codes, they are outdated, of course. They used to use some software called as Lingo, and you can easily skip those parts, right? But you can do all these things in Gecko, but fundamentals are very well covered here wherever they are expressed rightly. So basically it says that we know QT, DT and ET, small ET, for all the months of June, July, August, September and so on. And A naught is given and slope of that area capacity curve is given. Now all these terminologies must be familiar to you. And we have to minimize K. So what we do here, we calculate all these coefficients, 1 minus 80, 1 plus 80. This is how our end problem looks like. So they have not focused on spillover in first problem, which is fine. And they have not replaced RT with DT also. They are saying we don't worry about spillover, let it flow. Right? Even in that case, this continuity is right. We derived that. If you see here, although it looks like very intimidating maths, this is the same equation that you wrote. Now K is subjected to this. Release has to be greater than D and S has to be less than equal to K. Make sense? Now when you expand it, S1 becomes S2, S2 becomes S3, S3 becomes S4. And every time we are keeping check on release, and S1, S2, S3, S4, S6, they are all having their upper bounds. They have to be less than K and of course greater than 0. Right? If you just pay attention to the last equation, your S12 should be S13 and S13 becomes S1. Right? Looks very intimidating, but now these are just linear equations that you can solve using any programming language of your choice. You can even write a for loop for that if you don't want to write these 13 equations, and then just solve it. And once you solve it, you get the time series. That what should be the release in each month, what should be the storage in each month, and what is the capacity that you would need. Do you see that the capacity that we are getting here, 617.93, doesn't it correspond to the maximum amount of ST at any time t, which happens to be November? And no constraint would be violated if you have defined all the constraints very well, and it would make sense that reservoir will get full in November. And this is the real data, by the way. This is the data in Indian context for one of the watersheds in South India. So as we adopt our basin as Sardar Sarovar Dam, this professor, he adopts the Kaveri Dam as the basin on which he demonstrates all the examples. Right? So for them, the dam full period would be November. For Sardar Sarovar Dam, can you guess what should be the period when dam flows full?
September to October, September.
Around August to September. Right? But ultimately solutions would look exactly like that. You plot these on time series, you keep on solving them forever, you get your solution. That's it. Now he also solved it. So this is another thing I wanted to bring your attention to. If we solve it with evaporation, the capacity is 617 mm cube. This is not, of course, millimeter cube. I hope you understand. And if you solve it without evaporation, the change is around 588 mm cube. See the difference just by including and not including evaporation. Right? So this is a huge amount of water. Can you tell me how much kilograms of water it is? So this would be 10 to the power 6 meter cube, right? 1 meter cube is 1000 kgs of water or 1000 liters of water. So the difference itself is 2000 liters of water per meter cube. Around the difference is of 30 units. So can you multiply 30 with 1000? What that comes out to be?
So we can say na 30 billion kg, something like that, because we have million and 10 to
Okay.
the power billion, so 30 billion something.
if per capita per person demand is 150 liters, how many people can benefit from this water?
200 million.
Just from our evaporative losses, right? And Shazir, this also answers your question why we need to put balls or why we need to put ethylene layer on top of water surfaces, and why when we don't do that, we already see the repercussions for that. What is population of India?
1.3 billion and counting.
So evaporative losses of one dam is ideally good enough to meet demand for entire nation. But unfortunately, our dams, reservoirs, they're not interlinked. There is no concept of interbasin transfer. So it would just result in flooding if you take over measures to stop the rate of evaporation. Right? So it becomes a very interesting problem. What is good, what is bad kind of thing. And I don't have answer for that. Right? So if you, and then there may be concerns that you are disturbing the local water balance. Evaporation ultimately results in, comes back in form of precipitation, right? So it is sort of a distribution of same amount of water. Those who have learned hydrological cycle, we'll talk something about water balance, right? Water is not created, not destroyed. It is just going from one place to another and so on. But the point here is these losses cannot be ignored. If required, they need to be minimized. And sometimes it also helps. For example, Sardar Sarovar Dam is not a water deficit basin. Every year monsoon would come, it would flow full. And we want to minimize our basin size. So we want water to evaporate. Because if you do not let this water evaporate, you need a bigger dam. Bigger dam would mean bigger submergence. So again, there is no one right answer for a question. It depends from what perspective you are approaching that particular problem. Does it make sense? Any questions for today? And now if you see, I mean, we will talk about all these formulations in much better way without confusing, because somewhere they use dt and use the same equation, somewhere they use rt. Again, this is dt minus spill, of course. But we will go very systematically in all the topics that we are covering with minimum efforts, but with maximum understanding. Any questions? Yes.
So since we saw that evaporative losses constitutes of a huge impact on the reservoir size, so are there any dams in India currently which incorporates the strategies such as putting black balls on the surface of the water in the dams, as we have seen in foreign countries, or just you mentioned that as a oil substance? So why don't we currently do that in India?
Yeah, Bhaumik, from my personal experience, I have visited around 7 to 8 dams in India, which are of considerable size, including Bhakra Dam, Sardar Sarovar Dam, Hirakud Dam, and then in Bengal there is a dam called as Methan Dam. I don't know if you have heard of it. So, I mean, I have made extensive visits when I was working for industry. I could not find even one single dam where any kind of such measures are taken. And if these big dams don't have any provision, I am not sure whether small dams even think about it. Right? In
So
US,
we
however,
can save a lot of money out of that.
Huh?
We can save a lot of money out of that if we just use like this small technique.
Absolutely. I mean, so again, the problem with dams are that the amount of issues that surround them are already so much that our attentions are always to solve them first rather than dealing with those issues. You see that article that I shared, that dams could be solution to our climate change problem on our WhatsApp group, right? See the amount of positions we, huh?
So in Kaveri also there was an issue regarding this dam.
Every dam has an issue. So basically, if you read, there is a line in that paragraph, which it made me really angry. So the activists are saying, does not matter, we are still going to oppose the dams. But we think dam is going to be solution to climate change. So it is typical definition of activism, that let's oppose it first and then see what are the good sides and bad sides. Of course, no dam is perfect solution to anything. We have to agree there is a lot of displacement that happens, lot of environmental costs that happen instantly, but the long-term benefits are really different than what we just perceive in short term. And then there is no money that we can put to human life. We have to agree with that. And unfortunately, most of the communities that are displaced from dam sites are either tribal or socially vulnerable, and ultimately we think that they deserve to be displaced, kind of thing, which is a very conflicting objective. And ultimately you can never ever pay for somebody's origin roots in terms of money. So there is no easy answer for that. And it's not only in India, right? In US, when Hoover Dam was built, it was an area belonging to the Indian community there. So we are not our Indian, but the Indian community in US, the Aboriginals. And they were displaced and they were given money to build a casino. Can you imagine the kind of capitalism that we get into whenever we make these decisions, right? But more than money, the issues are primarily diverted on that side. And second thing, which is very alarming, is that in India, we still follow the practices for dam design that were laid by the Britishers or that were established in colonial rule. So the regional context is completely missing. If that is a policy, that is what we will read and we will implement. Finish. End of the story. So the contextualization has not happened yet. What is a trivial problem in some Western country may be the biggest problem in India whenever it comes to displacement or giving remuneration or displacing those communities. Britishers would not have worried about them. For them, it's India was a land where they invested, right? So people say that yes, colonialism had a positive impact, but we have to be take a very centered position when you look at these issues. That see these although this engineering came into existence, but ultimately it was for their good, not for our good. Our good was a side effect of their good, right? So that's what I say, that whenever you do all these optimization and all these things are important from academic perspective. And you all should know, your life is going to be much easier when you read any optimization paper after this course. And that has, I've already tested it with my students who are doing PhD with me. Right? It seems that why we are learning this, but when now they pick up any mathematics paper, it's a cakewalk for them. So retain those generalizations for them. It would not matter if you solve example 1 right or do example 2 wrong. I mean, for grade, it may matter slightly, but in long run, it's the understanding, the use that you can do in your other courses, that, okay, can we formulate it as an optimization problem? And then try to identify the solution, which is theoretically the best, because you can never do better than that. That is for sure. It gives you some lower bound against which you would be comparing your performances. After that, whatever you do, it is always going to have that flavor of realism. And I will end this class. I think I was in meeting with our director, Professor Jain, right? So we were talking about science versus engineering faculty. So he said that a science faculty should solve an approximate problem in an exact way, whereas an engineering faculty should solve an exact problem in an approximate way. And I think this one line summarizes everything that when we do in mathematics, right? Once these equations are there, it becomes a science problem. We have no flexibility to let any constraints run loose. If it is running loose, we cannot solve it. That's it. And our computer will also tell us this is infeasible. You cannot design this. But as an engineer, we always have to go towards that closest approximate solution that can save us, that can save the world. Yes, we are not able to fulfill these constraints, so let us let loose one of these constraints. And this would exactly become your class projects. That we will try to take highly ambitious problem. In next week, we should be defining that. And you try to come up with what are the constraints that are not letting us solve that problem. and where we need some interventions, be it from policy side or engineering side, where those approximations can be a bit relaxed and ultimately come at a solution which is not an optimal, but it's a Pareto optimal, right? So any questions before we go today? We have a few minutes. Today, I actually thought that we'll go a little longer because it has been a while since we interacted. And um, we will start with the stochastic programming or dynamic programming. I think you guys are now very much familiar. I want to spend some time on stochastic programming and introduce you to theory of probability before we start formulating stochastic programming. And from next week, that would be our prime topic. And I will post some questions as assignment in form of assignment that you can start working on. And now I will not ask you to write codes from scratch. You are free to use Gecko, you are free to use Python, whatever is easier for you. But don't start solving this using simplex tableau. It is going to take forever. There would be 30, 35 constraints. So recently I submitted a paper which is in review. There are 185 constraints, all linear. And of course, we use Gecko for that. All right, time for one more question before we go.
Like the dam gates usually have that opening thing, like from where we release the water. So like what happens when the water level is below that? How do we fetch water when that water level is below the gate height or what we say?
So Ruby, those gates are only for spillover. There are penstocks that are placed at the bottom. Penstocks are pipe of huge diameter. So when you look at cross section of a dam, just like so for example, can you see my tablet screen or no?
No, sir.
And now?
No, sir.
Okay.
Yes, sir, we can see.
So if this is a dam, right? Water is never withdrawn from here. Water is always withdrawn from here.
Okay.
There would be pipes here that would be running through the dam. Or there would be some tunnels, and the size of this tunnel is as big as the tunnel that you would see on a typical roadway. And these tunnels are designed to go for water. Here you will have all the turbine assemblies, and this is called as head race tunnel, HRT, and this is called as TRT, tail race tunnel. Whatever is the difference in water at top of this head race and tail race is effective head that is available for this turbine to run. Whatever
like
withdrawals are made for drinking water. So if you go to Sardar Sarovar Dam, you should take a complete tour. So they will show you from where Narmada Canal originates. If you haven't been there, plan it after lockdown. Or if you guys come back, we will go as a class there. So there you will see that all the withdrawals for usage are made just upstream. Nothing to do with dam.
Okay, so like when they say they've released this a certain amount of water, they mean that they have that spillovers thing. Like when they say they release certain amount of water.
Yes, and also there are double provisions for spillover. You would have these top gates, of course, and some dams there is a central gate also. So gate around the centroids, because sometimes it may happen there is a cloud burst in upstream, and these gates may not be sufficient to release enough amount of water. Ultimately, it's the discharge. It's not the volume; it's the rate at which you are discharging the water. So when they say all gates are open, that means these gates are open, these gates are open, and there is a short circuiting that they have done between head race and tail race. So short circuiting is will not use anything, let the water run, because if that doesn't happen, this dam may break or there may be a flooding upstream. And that is what I'm teaching you guys, right? That what is the impact on upstream, downstream when you obstruct a river, right? This is exactly obstructing a river, and we quantify, I mean, the amount of control that we have as civil engineers on our understanding of this H1 and H2, you would be surprised to know and learn when we do some derivations. Not only that, if you give me a dam, water is flowing, you tell me an obstruction, I would even tell you that why the profile is going to look like this, or profile is going to look like this, or it is going to be a straight line with so much accuracy that this profile is actually going to be like that if my observations are right. Because it is going to have a huge difference. You saw that neglecting 7 mm per day of losses results in such a huge difference. Imagine if we get these profiles wrong, the flooding profiles wrong, it could mean that an area would be totally submerged underwater, or it would have no impact whatsoever for the dam. Or it may actually sort of becomes, so there is a village and there was a water at that particular level, and now water has suddenly dropped. It just living along edge of a cliff, right? If you go around Hoover Dam, you just watch some documentaries on Hoover Dam, you see the upstream. It is typically cliff, that if you stand there, you see it's an abysmal or bottomless depth that you're staring towards. And in countries like India, where every part of our nation is populated or having some density of population in different pockets, you cannot just create all these profiles without knowing how this water is going to react. So starting next week, all of you will divide yourself in team of 3. This is a very small assignment. Team of 3, each team next Saturday will talk about any hydroelectric power plant project of their choice. And it should not be a boring presentation. Something interesting should have happened with that dam. Either that dam was met with a lot of opposition from social perspective, but later on proved to be an engineering blessing. Sardar Sarovar Dam is a good example of that. Or it was all the opposition for right reasons. A dam in Brazil that I think broke last year was a good example of that, right? So identify some of these interesting stories and come up with the key question, key gap you can ask using this understanding of optimization or understanding this mathematical modeling, that what interesting things still are left unanswered or how your mathematical modeling can help you address those. Don't make it a typical academic exercise again. Do it for fun. Do watch some documentaries, do some Google search, find some photographs. I will not hold you responsible here for plagiarism. In the sense, if you find an image, don't worry about adding a citation there that, oh, this belongs, because this is only for our internal use, right? Don't spend 30 minutes in making a presentation and 1.5 hours to add the bibliography, right? Spend 1.5 hours to make presentation and 30 minutes to check whether it's consistent or not. So let's make it more open-ended, basically. And it's all up to you how you organize yourself in team of 3. What is the size of this class? 27. So 27, yeah, 9 teams, 9 dams are there which are worth considering. So my recommendation, please cover this 3 gorgeous dam in China, 1 in Brazil, one of course our Bhakra Dam, and 1 Sardar Sarovar Dam. Look into why these dams were even built. So these are 4, and identify 1 dam which was built purely for military reasons, and it would be somewhere between India and China. Right? So basically look into all aspects, and next week we will have some interesting presentations from you. And all 3 should cover different aspects. One should look into hydropower, one should look into societal aspect, and one should look into the water distribution aspect. And all these dams would have at least that impact. And do some interesting calculations. What would happen if this dam breaks? What area would be under deluge? Right? So, and this is easy to do. There, you know the capacity of a dam. If you do some distribution of certain depth, you should be able to know what is the area that would go under submergence. Stand at that area, draw a circle of that radius on a map. You should know your land of submergence. Make sense? All right. So I will post one academic exercise, and this is a non-academic exercise, which will also be graded. Don't think that you're doing it for free. It would have some grades. So do the best job there. Team of 3, 9 presentations next week. Thank you.
Thank you, sir.
Yeah.